Hi everyone, welcome to the Recurrent ETDS seminar. Today we have Gaurav Aggarwal and he'll be telling us about orbit closures and random walk. Over to you, Gaurav.
Thank you for the introduction and thank you for inviting me. Today I would be talking about the orbit closures and random walk. This is based on a joint work with Professor Anish Ghosh. So the central theme of my talk would be that we are given a topological space X and we have some semi-group H acting on X, and what we want to do is that we want to study the action of H on X. And in particular, the question which I would be focusing in this talk is that can we somehow classify all the orbit closures of this section? That suppose I'm given a space X and given a group semi-group H acting on X, can we somehow able to say for every X that H dot X closure would look like something like this in a certain category of sets? So this is the question I would be interested in. In general, this question is quite vast, and complete classification is not possible. And this question has a lot of applications as well. For example, in Teichmuller theory or number theory, representation theory, GGT, or many others. In this talk, I would be only restricting myself to the developments that happened when X is a homogeneous space or in homogeneous dynamics. And so I would be discussing a few major development that happens when X is a homogeneous space, and can we classify or not the orbit closures. Then I would move to the result which we proved in joint with Anish Ghosh, and give some applications of the result we proved to the number theory. Okay, so let's proceed. In order to, since I already mentioned that the problem in itself is quite actually vast and a complete classification is not possible. However, in certain cases, the classification is possible. And so let me just start with an example to get a positive start that in many cases the orbit closures is actually nice enough and we can actually classify them. So the simplest example is given by when X is a torus or R mod Z, and the action of the natural numbers of the semigroup is just given by the translation. So theta goes to theta plus alpha, theta plus 2 alpha, theta plus 3 alpha, and some for some fixed alpha in real line, and we want to classify the orbit closure for this section. And in particular, it's known that if alpha is rational, then the orbit is actually just finite for every theta. However, if alpha is irrational, then the orbit closure is actually the whole torus for all theta actually. So in particular, this case, it's possible to classify the orbit closures. Another positive example is when we take two torus and take a fix some alpha beta and consider the action of real line on this torus given by just the translations, like theta 1 theta 2 moves in the direction of the alpha beta via time t. And in particular, in this case as well, the classification is possible according to whether the slope is rational or irrational. If it is rational, then the orbit is actually closed and it's given by some rational subspace which is kind of moved with the theta 1 theta 2. And if it has an irrational slope, then it actually becomes dense. Okay. The third and a little non-trivial example is that when we consider the space SL2R modulo SL2Z, which is the coset space, and we consider the action of the group, the unipotent group, the strictly upper triangular matrices, and we try to study 1x018 dot SL2Z, the coset ASL2Z. And in this case, actually the orbit closure again can be completely classified. It's either periodic, that there exists theta so that it closes up, or it's actually completely dense. Okay, and so I've discussed some example in which case the orbit closures can be completely classified. So let's give an example in which it's not possible, or in which it looks completely weird. So consider the example, okay, it's R mod Z, so it's T, sorry, there's a typo here. Suppose X is R mod Z, again the torus, and now the group is changed to Again, natural numbers, but the action is given by multiplication by 3. So it's n theta plus z goes to 3 to the power n theta plus z. It's multiplication by times 3 map. And as many people already know, this is isomorphic to the shift space on 3 symbols. So the dynamics is actually very, very complicated, and orbit closures can look as complicated as we want. And in particular, it could be something like full torus, could be just rational number, could be middle third candidate set. And in particular, given any real number alpha between 0 and 1, there exists a theta so that the orbit closure looks like has the Hausdorff dimension alpha. So in this case, the orbit looks as wide as possible. However, if we just, instead of looking at n action, we look at n square action. And instead of just looking at times 3 maps, we like look at times 2 times 3 maps like simultaneously and study the orbit closure. It is a well-known result by Furstenberg in 1967 that orbit closures either is full torus or just the rational numbers. In particular, what we have seen through these examples is that even though the space is same, more or less, I consider the example in which we were studying the torus. As the group action changes, the orbits can look extremely different and vivid. So in particular, question comes that the dynamics more or less depend a lot on the acting group. How does it act? Whether it act in a certain way or the other way. Like over there, it's translation or something. Here, it's a multiplication. So a lot of difference comes up. So a question is, can we somehow classify all the groups which has nice closure properties? Is there something common in between them or something? So one of the first well-known, like most famous result in homogeneous dynamics is that unipotent act nicely. This was a conjecture of M.S. Raghunathan and was solved by Ratner, and it's now known as the Ratner's orbit closure theorem, which says that if the acting group is generated by unipotents, then the closures look nice. So let me just first of all define what actually I mean by the unipotents. So I hope everyone knows about the adjoint representation, but let me just remind what it means. So suppose G is a Lie group, connected Lie group. In fact, by which I mean it's a topological group and it has a Riemann structure so that it maps are continuous and differentiable and everything, the multiplication and everything. And G denotes the Lie algebra of the group G. And consider the map from G to G given by H going to G at G inverse. Fix G and consider the map from capital G to G as H going to G at G inverse. This maps takes identity to identity. So in particular, we can take the derivative of this map at identity, and this becomes a linear action on the Lie algebra G, so the group G. So it's an element of the G, the group of all the linear matrices acting on the linear algebra, invertible matrices acting on the vector space G. So this gives a map from the group G to the linear invertible matrices on for the vector space G. And this is called as the adjoint representation. Now, by unipotent element, since I said that the Ratner theorem is that unipotents act nicely. So what do I mean by unipotent? An element is called unipotent if adjoint G, when viewed as a matrix over here, is actually a unipotent matrix. I mean, adjoint G minus identity to the power n becomes 0 for some large enough n. Okay. So the Ratner's theorem tells us that suppose I have a group X is a homogeneous space, by which I mean X is G mod gamma, where G is some connected Lie group and gamma is a lattice. So for the people who doesn't know what a lattice means, it means a discrete subgroup of group G, such that G mod gamma, the fundamental domain, has some finite volume, has finite G invariant volume. its definition is a little technical, and for those who is seeing it for the first time, since it's not the main topic of the discussion, I have planned to skip the definition. So, but there are very nice articles written about the Ratner's theorem. The people who want to know, for example, the book by David A. Morris is one of the excellent reference for the Ratner's theorem. But let me just proceed directly now. So it says that if X is G mod gamma and H is a connected group which is generated by the unipotent elements, in this case, the orbit closures can be completely classified. In particular, when we were in the torus case, since the action is abelian, so every element just goes to identity. So every element acts by unipotent. So in that case, the example 2, 3 is one of the consequence of the Ratner's theorem, which tells us that the orbit closure is forced to look nice. It looks like a manifold. It looks like some other homogeneous subspace contained in G mod gamma. So now we already know using the Ratner's closure theorem is that given a unipotent, it acts nicely. The orbit closure looks nice. Now the next question is, okay, just before I forget this, Ratner's orbit closure theorem also has an applications to Oppenheim conjecture and many facts in number theory. Okay. The next question is, what happens if H is actually not generated by unipotent but is a diagonalizable group? And the question is, can we similarly classify? The answer is no. It's not usually possible to classify the orbit closures for the diagonalizable group. In fact, if we consider the simplest most example, which is SL2R modulo SL2Z, and if we try to look at the diagonal flow, then for every alpha, like the orbit closure can look as wild as we can imagine. In fact, for every alpha in 1 to 3, there exists an X so that the Hausdorff dimension of the orbit closure is actually alpha. So the orbit can look as fractal-like structure as we can imagine, and it's completely chaotic structure. This is similar to example what we did for the times 3 map, which where it happened that the if it consider the torus and times 3 map, then the orbit closure could look extremely wide, and for every alpha in 1 0 to 1 we had like the orbit closure looked like could have dimension alpha. But as we added the times 3, it became really nice. So the natural question is, what happens if we look at the higher dimension, so that we have more diagonal group, the rank of the diagonal group is more than 1. In this case, in this particular case, it's a conjecture and it's not yet solved, is by Cassel, Swinnerton, Dyer, and Margulies, is that given any x over here, its orbit is either unbounded or periodic. We are not even saying, it's not even known that it equidistributes or something. It just is asking that if the orbit is bounded, it should be periodic. And even with this development, the current progress is we can't really classify this result. However, a significant progress has been made towards this conjecture, mainly due to Einsiedler, Katok, and Lindenstrauss, and they have proved that a set of exception sets for which the orbit closures are not known are have very low Hausdorff dimension. And one of the key tool they use to prove or discuss this statement is the study of the invariant measures.
Can you go back one slide?
Yeah,
So, when you say unbounded and periodic, till now you were saying something like full group, or it's
yep,
either the complete group or it's a nice subgroup, uh,
yep.
or something of that sort. So here, like you don't make any such statements, or this is that is a question you ask later. Like right now, even this is.
Yeah,
Uh,
even currently, even this is unknown that whether we can prove something like if it is bounded, then it's periodic. Like even a very weak statement like this is not possible like using the current tools. So a complete classification is completely feel out of hands to discuss.
Mhm, mhm, mhm.
Yeah,
Okay.
that's like earlier we were discussing that the orbit closure looked like this particular, but as I say, it could be very chaotic. So
Mm.
currently we can't really say anything.
So just another question. In this
Yeah.
sphere of things, when we are talking about classification, is
Yeah.
there, one way in which you describe that there's no nice classification is by saying that you can get something with any Hausdorff dimension in
Yep.
between in an interval or something of
Yep.
that. So there's another kind of classification results which, essentially, yeah, where you talk about um, what kind of dynamical systems appear essentially.
Okay.
So up to conjugacy or some such maps, for example, Shilpagda probably knows a lot more about this than I do. Like, are there any anti-classification results in this sphere that under certain things, like it's not classifiable?
I'm not aware, honestly. I'm not aware.
Okay. Like, for example, with your example on R mod Z, for there,
Yep.
like that unclassification result applies there, but I have no idea whether it applies anywhere else.
Okay.
But
So in the case of like shift on the finite symbols, you say
yeah,
that
yeah, you can't classify what are the minimal systems up to conjugacy.
you can or you can't, sorry.
You cannot.
You cannot. Okay.
So there's
Okay.
a very specific mathematical statement related to this. Like, I'm just curious. Yeah, I was just curious if there's any such thing known in other cases.
On honestly, I haven't read anything like
Okay,
this
all
so
right,
far.
sure,
So
sure.
yeah. Okay. And yeah. So as I was saying, the a significant progress in this statement towards this conjecture has been made, and mainly due to Einsiedler, Katok, and Lindenstrass. And one of the key strategy they used, and also the strategy which was used in the Ratner's theorem, is to study the invariant measures. So what exactly do I mean by the study of invariant measures? So a measure mu on a space X is called a H invariant measure if for any set measurable set A, take its P-inverse under the some element H in H. So it should be for all H in H as well. H inverse A. The measure of that set is same as the measure of the current set. And why we want to study this kind of measures? The reason is that many cases, in a lot of cases, it's possible that the set H dot X can always be equipped with the H invariant probability measure, who support actually exactly equal H dot X closure. So in particular, if we are able to classify all the H invariant ergodic probability measures, we are almost able to classify all the H orbits of in the in the topological space X. Now, some examples where this can always happen is when the group H is abelian or something, or amenable
Excuse
or
me, can you explain the last point why classifying measures is enough?
so. For example, in Radner theorem, it happened that the ergodic measures for the space exactly look like the orbit closures. Like there exist S dot X, for example, in Ratner. What happened is that if we try to take this u as one parameter flow, and we try to look at the orbit closures of integral from 0 to t of the, I take the orbit along the r action and we put the uniform measure on it and suitably normalize so that it looks like probability measure, and take the weak limit of this thing. It exactly looks like the Haar measure on this homogeneous space S dot X. So in particular, what I know is that using this, because H dot X would be contained in S dot X, I get that orbit closure must, so it gives that H dot X closure contained S dot X using that thing. But then other way around, you can possibly say in other ways as well. And in diagonalizable group also, because you know that the orbit closure would roughly contain the initial points, you get that the orbit is the support of the measure, the weak limit measure, the classification you get actually gives you the, sorry, what was I saying? The support of the measure exactly correspond to the orbit closure. You have,
Okay.
yeah, there are a little things you need to do in between, but this thing, if you can classify all the H invariant probability measure, it's like one of a very essential step, and like one of the most important tool you can use to, for example, say that how does the orbit closure look like. For example, in case of this conjecture, it was proved that use proved that if the measure is invariant under the diagonal flow, and if you can say that it has positive entropy, then you know that it's actually hard by the result of Einstein-Lukatov-Lindenstrauss. So if you start with the point x and take the start putting out some measure on the its orbits and uniform measure. So if it and take the weak limit, if it converges to zero measure or it's not a probability measure, then you already know that it it's unbounded. And if it converges to a probability measure, you know that if it has positive entropy, then it's hard and unbounded again. If it's periodic, then also. So in a lot of cases, a lot of results are known due to this statement. Obviously, you have to do a certain results here and there, not just trivially it gives you. And in particular, this result, the classifications tell you that what are the Hausdorff dimension of the exception sets of the this conjecture is bounded by, for example, in this case, 2 or something locally. Okay. Two corresponding to the fact that if you have X point and you can take it in the diagonal direction, and you still would have an orbit which is not bounded and not periodic. Okay. How,
Okay.
even though, yeah, even though this strategy is quite useful and has a lot of application, it has some setbacks as well. For example, in some cases, the orbit closure, the study of it is far simpler, and classification could be very, very difficult. For example, the discussion I made about the 2 to the power n theta, 3 to the power n, this section, although we already know what the orbit closure looks like, the study about the invariant measure is not known yet. It's still a conjecture and was made by in 1967 by Furstenberg. Is that any measure invariant under this semigroup action is either the Lebesgue measure or is finitely supported, like 1 or 2, 0 or 2, like just those. And people still don't know how to prove this. Like this is one of the very interesting question which people have, and like in homogeneous dynamics, and some results are known that if it has positive entropy this that, then it's hard or something, but otherwise it's not known. The other setback is that even though in a lot of cases you have an H invariant measure on H dot X closure or orbits, in many cases you simply don't have. For example, if I consider the torus R2 mod Z2 and I consider the action of SL2Z, then guys can take it as an exercise is that there is no actually H invariant probability measure on the torus. So we can't really classify the invariant measures. So how do we classify the orbits if we want to use this strategy? So one of another technique which is used to overcome the second factor is, which was that you don't have an H invariant probability measure, is that you study the stationary measures. So what does stationary measure mean? Stationary measure, in many cases, H dot X closure, even though doesn't contain H invariant probability measure, it contains a stationary measure. And if you can classify, I will define what a stationary measure means, but if you can somehow classify all the stationary measures on X, you are in a good shape, because then you can classify in a lot of sense the stationary measures on the group orbit closures of the action. So let me just recall what does convolution mean and what does stationary measure means. So a probability measure. So I've written measure, but in the coming slides. But remember that I would be assuming that whatever measures I'm assuming from now on would be probability measures. So I won't repeat this. So what does a probability measure on X means? suppose I have a measure over here. One way to think of it is that it gives us a law of picking a random point from X. In particular, the fact that that random point belongs to this some measurable set A is exactly the measure of A. And now, suppose I have a measure mu on X and a measure nu on group G. So with respect to mu, I can pick a random point X in this space X. Using the measure nu, pick a point G randomly with respect to nu and move it around via the action of G. So consider this point G dot X. Consider the law or the probability measure on this X, which is given by the fact that the random point chosen is exactly given by first choose a random point with respect to mu and then pick a random point with respect to nu and look at this G dot X point. The law of choosing this random point is exactly the convolution of nu and mu. To see this, or what does this mathematically this convolution means is that the probability of random point chosen belongs to the set A is exactly the probability G dot X in A, which is same as measure of X or measure of integral over X and G of the fact that G dot X belongs to A. And if both these laws of picking random points are actually agree out, then we'd call that the measure is actually invariant under the action of G. This is a geometrical description, and many people might be a little uncomfortable with it, but that's how I think about the stationary measures. A much simpler way, what people actually much more like or much more have seen, is that mu is actually equal to nu star mu, which is actually equal to G star mu d mu G. And a measure is called as mu stationary if this equality actually holds. But another way, a geometrical way of thinking about this convolution is that the random point given by this mu star mu is given by picking a point with respect to mu and then picking a point with respect to nu and moving it around via that. So this is called as stationary measure if both laws agree or if the measure mu is actually equal to the integral of G star mu d mu G.
Perhaps a
Now,
third perspective is that you're running a Markov chain where your law over the group G is being given by nu, and yeah,
Markov
which
process is there, but it's much more difficult to introduce. That's true. It's way more
it's much
generic.
easier. Depends who you talk to, but anyways.
And the idea is that can we classify all the new stationary measures? So this is the question we would people have checked or like now is interested in order to study the orbit closure. And this question has a long history and a lot of developments happened very, very recently around this area. Starting the results started from the works of Bergen, Fermat, Linus, Moses, and simultaneously around by Benoit and Kahn, where they study about on torus and homogeneous spaces about the orbit closures. Then Iskin Mirza Khani in 2018, where they study about on flat surfaces. Then Eskin Lindenstrass, which is an unpublished paper, which is the most general result we know this far. Simmons Weiss, Sargent, Shapira, like they all discussed a lot of cases when X is this space, gamma is that space. They studied the orbit closures and classified the stationary measures. In particular, Bernard He and Zhang and Bernard and Zhang proved the effective equidistribution of random walks as well. And recently also Khalil Weiss, who also discussed this random walks on periodic spaces and others. However, a common feature in all of these random walks so far studied, and except the last one which came out recently, the Khalil Weiss, was that they have a common property, which was that expanding property for adjoint action. So what exactly that means? So as usual, the D denotes the Lie algebra and adjoint action as I defined with the derivative of the conjugation map identity. Then we say that a measure mu on the group G is said to satisfy the expanding property if I take any Lie algebra element V in the group G. So I take an element V in G, and I take randomly elements in group G with respect to this nu to the power n measure. So G1, G2, G3, G4, Gk. And I try to look at the log of adjoint of Gn, G1, Gv. It should be positive. The limit n tending to infinity, I missed it. Limit n tending to infinity of 1 by n log of the adjoint action should be positive. What does this mean is that I take a vector v in the Lie algebra and act it randomly via elements of the group G. Then this vector v should expand exponentially. It should grow, and it should grow exponentially fast. So this is the mean, and it should happen for all v, not just for some v. It should not happen for it should happen for all v. So in particular, the diagonal groups are completely cut out because they have a contracting direction. Like you have certain contracting directions, and unipotents are also cut out because they have a polynomial group. So this studies the case which are intermediate between those two cases. And with this assumption, a lot of results, like all these prior results, assume that the random walk satisfied this condition. In the joint work with Anish Ghosh, we studied a random walk which does not satisfy this property of for the adjoint action, the expanding property. I won't be able to, due to some technical issues and some other setup that's required, I won't be able to state the most general statement, but I would give a baby example of the result which we proved. So the baby example of the proof is, the baby example of our main theorem is that consider the group G is equal to SL2R mod semidirect R2, SL2Z semidirect Z2, and X is G mod gamma. And consider the measure mu on the group G given by the uniform measure on the elements 3, 3 inverse 0, 0, 3, 3 inverse 2, 0. So in particular, you can consider it as a question that we want to study the orbit closures under this action, but our main interest is that how does this random walk look like? And we want to study the stationary measure for this mu action. And to see that this is actually non-expanding, you can see that the vector over the Lie algebra corresponding to element over here in the lower triangular would actually be shrunk, like it will be contracted under this section, the diagonal flow action. So it's not an expanding random walk. So and so it's not an expanding random walk. So we had like the assumption about the expanding random walk is actually very crucial. And in order to compensate for that, we had to assume an additional condition on the measure mu, which is that suppose mu is new stationary measure, it satisfies an additional condition that it's projection under the natural map from SL to R semidirect R to modulo SL to Z semidirect Z2 to SL to R modulo SL to Z, which is given by AB SL to Z semidirect Z2 goes to A dot SL to Z, is actually hard. So let me just unfold this thing much more clearly. So the space we are looking at is SL to R semidirect R2 modulo SL to Z semidirect Z2. This space actually is a torus bundle over the much more simpler space SL2R modulo SL2Z. In particular, if we are studying the random walk, which is given by 3, 3 inverse star 0, it actually gives a deterministic walk on the base space. It's just, if I take an element in the above space and move by a random walk, if I look at its image in the base space, it's just moving by the 3, 3 inverse. Like the elements is not changing, whether I take over here 0 or 2. So it's a deterministic walk. So if I'm trying to study the stationary measures on the above space with respect to the random walk which I have stated, it's actually same as it would imply a classification of all the invariant measures for the diagonal flow. And as I stated, the study of the invariant measures for the diagonal flow or the orbit closure is way more complicated, and the complete classification is extremely difficult. So the assumption that it projects to the Siegel-Haar measure on this space is actually to compensate the fact that over here the things are nice. So we proved that if on the base space the things are nice, that it's the Siegel-Haar measure, that we are not getting trivial difficulties, then on the top space it's actually also Haar. Another way to diagrammatically look at this thing is that suppose I consider the SL2R modulo SL2Z space and I start from a point x0 and I move under the diagonal flow, so the deterministic walk 3 inverse, and I look at its trajectory and suppose it actually equidistributes in this space. Then I take any point on the torus, so I'm making a torus bundle. I take any point over there. I have the random walk. So I can choose either of these 2 points, like Markov process, as Nishant suggested, like either moving via the 3 inverse 0 0 or 3 inverse 2 0. Like these two choices. I move along one, then I move randomly along two, then again. If this actually equidistributes, then the orbit at the top is also equidistributing in the torus bundle, almost with respect to the random walk, like with probability 1. And in particular, it gives the orbit closure under the random walk. What does it look like? Okay. A particular application of this result is in the fact that how does the unstable directions look like. So I would be saying some words, which might be a little like for the a little expert audience now. So we already know that if we pick an element randomly with respect to Zine real line, in the if we take the full unstable direction and pick a random point over there, and if we have a diagonal flow, and if I take the full unstable direction, I pick any random point, the orbits get equidistributed in the full space. Question is, what if I don't take the full unstable direction? I take a subspace of it. So I'm fixing A and letting Xi vary. So it's a subset of the unstable direction. What happens about the equidistribution statements? So this becomes difficult. Our results gives that in this case, actually take the real line, it's going to equidistribute. Secondly, in particular, replace this real line by a fractal as well. You still are going to get that almost surely it's going to get equidistributed. So this significantly changes the that fact about the unstable directions and equidistribution statements. So in particular, for what I mean to say is that suppose I take a point x naught in the base space, which is actually getting equidistributed. I look on the torus bundle, I pick a point randomly with respect to self-similar measure. So this is T2, like torus. I pick a point in the first coordinate given by the fractal, some random point, and second coordinate to be xi 0, and move it under the diagonal flow. Then its orbit actually looks dense. It equidistributes. So it tells that on the base space, if you have an equidistribution, on the top space, you pick a random point, you're also going to get equidistribution. Even the point is chosen with respect to some fractal measure. And it has applications to inhomogeneous Diophantine approximation. So, which is the almost the last part of my talk, is the following. So, inhomogeneous Diophantine approximation. So, what does that mean? So in Diophantine approximation, the main interest is that we are given some real number theta, and we want to approximate it via the rational p by q. For example, pi by 22/7 or something like that. This theta being approximated by theta minus p by q being small can be written as p plus theta q being small. So in particular, we can just replace theta by a matrix and q by a vector and p by a vector. And what we are asking is p plus theta q being small. The inhomogeneous Diophantine approximation is that we are not trying to make this 0, but we are trying to make this as close to another vector xi. So in inhomogeneous Diophantine approximation, the main interest is now fix theta a matrix and xi a vector in Rm, we are trying to look at p plus theta cube plus xi, and we want to make it small, while the denominator q, we want that it's not actually very, very large. So this is one of the goal of the inhomogeneous Diophantine approximation, to approximate xi by the zm plus theta zn. And the result tells us that suppose I fix theta, which has some nice enough dynamical properties, some nice properties, then the pair theta comma xi is forced to have nice properties as long as xi is picked randomly with respect on a self-similar fractal or any particular point or just the real line or anything. The orbit or the pair theta comma xi is forced to have the nice Diophantine properties. That's what is expected. Like if I pick theta and xi randomly with respect to the Lebesgue measure, a certain expectation is that it behaves nicely, that the number of approximate is this, it's not bad, it's not very good, it's like just the simple Diophantine approximation, some nice property. That's going to get descended to the fractals. So one of the key results which we proved is that, which could be like taken a takeaway of this inhomogeneous Diophantine approximation part, is that we are able to descend the properties from the real line to the fractals, the inhomogeneous properties and the dynamical properties. The properties which was known for the real line, we proved the analogous properties for the fractals. And in particular, using this, we were able to answer a question posed by Moshevit and Rao and Shapira, and proof also partially answered the question posed by Solan and Visser. And thank you.
Let's thank Gaurav for this wonderful talk.
Thank you.
Any questions from the audience?
So,
Right.
I don't know who started speaking first, so
I think
maybe I'll
Anubrata.
give the younger person a first go. Anubrata, go ahead. Actually, I don't know if you're younger. I'm assuming you're younger.
no, yeah. So in the long history,
Yeah.
right, they use this expanding property of the vectors grow exponentially. So
Yep.
inducing the invariant measure, does it go through construction of some kind of a transfer operator, or something like a Rowell-Perron-Frobenius operator? Is that something any of these papers do?
Sorry, can you come again?
So I'm thinking of this condition like hyperbolicity. If the derivative grows exponentially in one-dimensional dynamics.
Yeah.
So in that case, you'll probably have a Markov partition so that you can get shift in and you can then do the transfer operator to get a Gibbs measure. So that's the
No,
template at least. Oh, they don't.
no, there is no Gibbs measure or anything. The main strategy is to prove that the leafwise measure under a certain, like we would be studying the Lyapunov exponent and the Lyapunov direction, the most expanding directions, and the study is based on proving that the leafwise measured along this expanding direction is actually invariant under certain unipotent. And then actually we go to the Ratner to say that, okay, the measure mu can be actually uh, decomposed as an integral of the homogeneous measures, and then we are able to say. So it's called exponential drift. So we usually don't use Gibbs measure or something. I haven't heard about it.
No,
Maybe.
I was asking about the papers you cited as the history in their work, where
Okay.
you have that expanding property.
Okay.
So do you know that if any of those use a technique of the sort I said about?
It might be possible on in this Eskin Mirzakhani, but I think the other papers, I think I have taken a look vaguely around them. I don't think anyone has used. But Eskin Mirzakhani, I think so. That's like infinite volume spaces, and something like this might be true. But other papers, I'm not like Other, I don't think so.
Okay. And I had
Yeah.
another question. So, can you explain how Furstenberg's proof follows from Ratner? I think you explained. Can you explain that again?
Furstenberg's proof follows from Ratner. No, it doesn't.
So the 2 to the power m, 3 to the power n, did you say that? Oh, it does. Oh,
2 to the
you
power.
okay,
Do you
okay.
mean
No,
the
no,
Sorry.
no, no, no,
conjecture
no,
or do you mean
that's
the theorem?
No, the theorem you
There's
prove.
the theorem.
Once
The one about topological.
yeah, 2 to the power m, 3 to the power n.
yeah. This thing does not follows from Ratner. This is a like look
Okay,
like a
okay, I misheard you.
diagonalizable. Yeah, it's a completely different proof and like yeah, it's like a diagonalizable action. Like people, yeah, it's a completely different altogether story.
So can you explain how Furstenberg proved it then? In short.
Oh, I have no, I don't know. It's a difficult proof. Sorry.
Okay,
No.
okay, okay, okay.
No,
Yeah.
this one is actually a very nice proof. I recommend you look at the paper directly, Anubhato. This is something you
Which
can
which
actually sit
which
on and read. This
which paper is this?
1967 paper.
Okay.
It's a classical paper in ergodic theory. Every
Yeah.
ergodic theorist should read this. Anyways,
Okay, I will read it. Yeah.
other questions?
I just wanted to have a second look at the last but one slide.
This.
Yes. Okay, another question is this flexibility result that you told about the host of dimension. Can you go to that host? You can get everything between 1 and 3.
I think that's due to symbolic dynamics. That's because the shift space is isomorphic to
Uh-huh.
the shift symbols on two, and then you construct orbit by hand to get the, for example, you want the Hausdorff dimension, so you can choose that this orbit is not there, this orbit that, and you can construct in between.
It's like
Well,
entropy arguments, right?
Yeah.
Yeah.
I mean, my question is like, is this 1 and 3 hard bounds, or is it like what is done?
Which 1 and 3, which one?
So this there was that result between the Hausdorff dimension is between 1 and 3.
Yeah,
So
that thing.
yeah,
That
so
is this thing. Yeah. Yeah, this thing.
yeah,
This is because
so
the SL2R modulo SL2Z is actually the suspension over the
okay, sure.
the shift
Mm.
space on the infinite symbols. It's take an invertible extension of the Gauss map, and it's a suspension over there. So
No,
you have shifts.
yeah. So what I'm asking is that like is less than 1 possible? I mean,
No,
say
because one dimension is given by H, right?
okay, yeah,
It's a
sure,
real line.
yeah,
Yeah.
okay, sure,
Yeah.
okay, thanks.
One is possible.
Mhm.
I think so.
Any
Just
other
take the
question?
divergent.
So it's as good as it gets, I think. I mean,
Yep.
yeah.
Any other questions for Gaurav? So Gaurav, just a general question. So I don't know if I should start with an example or a general question. Let's start with the general question. So I'm essentially thinking of all these random walks and what your am I correct in saying that you want to understand stationary measures for various random walks under assumptions on the random walk that
Yeah.
yeah. So uh so it's kind of fascinating. You have this step up kind of result that if you know something for, well, I don't know, step down or a step up result, that whichever way you want to look at it. But here's a general question. Suppose but your eventual goal is to classify, say, H invariant measures, right? That's your eventual goal. So suppose I know the result for sufficiently many random walks.
Okay.
So anything which is invariant under H will be invariant under your random walks as well. That's
Yep.
obvious.
Yep.
So now suppose I of course, now if I know it for sufficiently many interesting, I'll call it transition probabilities. I hope this makes sense. Transition kernels.
I think
Uh,
I can. The main thing actually happens is that why we study the stationary measures is because we don't have invariant measures. So,
right,
hope of getting invariant measure using stationary measure is, I don't think so possible, because if there were edge invariant measures at the start, because for example a minimal group or something else,
right,
then we would have like studying the random walks is actually much more difficult. We would have started with the stationary measures directly to get much more nicer properties, because any tool
right,
being applied for the random walk can be applied for the stationary measures already, because sorry, invariant measures.
right. So it's sort of, but for now, I guess the kind of things that we are looking at, we don't know if there are invariant measures. Like we don't have a classification of invariant measures, right? That's the issue. Uh,
Classification of what?
Invariant measures,
Yeah,
like,
yeah, yeah.
yeah. So, right, but in, I guess, right. So somehow knowing enough about, suppose we know like invariant measures for a bunch of kernels. You're saying that this will not necessarily shed any light on the actual invariant measures for the actual semigroup. This you don't.
For example, this SL2Z on action
Mm-hmm.
on R2 mod to T2,
Mm-hmm.
there's no invariant measure. We can study
Right.
about
So
a
you'll
lot
always
about,
have stationary. Yeah, sure.
you can say a lot about the orbit closure, how does it's gonna act, this, that, but
Hmm.
if they don't exist, we can't really say anything.
Right. No. I agree with that. I agree with that. That you'll always have interesting stationary measures, but and I know you mentioned in the beginning of your results that you will concentrate only on probability measures.
Yeah.
But does this shed any light on other measures? Because that's another way to look at orbits, right?
On infinite volume homogeneous spaces, there are results known about the random walk. Unfortunately, I haven't read them so far
Mhm.
because, yeah.
Sure, it's
But there are works done on the random walks on infinite volume homogeneous spaces as well, and other results, everything.
mhm, mhm.
For example, one of the work of, I think even, yeah, so people are also studying, instead of just the homogeneous space G mod gamma, they are considering something like G mod H, where H is some other group, like it could have a connected components, for example, some solvable group and modulo SL2Z, or some discrete part and a continuous part. People are studying that also. I've read some of the work. So as I stated, like in order to motivate the result, I just take a small set of examples where, or the major themes of the work. But yeah, there is a lot of research going on, and a lot of results are known in many cases and others, like as you're saying, the infinite volume spaces or other possible scenarios, but I'm not aware.
No. Okay.
Yeah.
Other questions? Okay. Thanks a lot, Gaurav.
Thanks a lot.
Thanks.
Thanks, Gaurav.
Thank you.